Alright, video 3, and as you can still, I still have an eraser here as a pen, but again, if it works, it works, so we're going to go with it. At least it's got something. Um, Alright, evaluate the line integral, f dot dr, where f is x, y, y, z, z, x, and c is the triangle with the vertices given as 1, 0, 0, 0, 1, 0, and 0, 0, 1, oriented counterclockwise as viewed from above. So let's go ahead and take a look. First of all, whoops, that was really bad. Let's take a look at what this looks like. I mean, it's pretty basic. So, vertices 1, 0, 0, 0, 1, 0, 0, 0, 1. I missed. Close enough. Makes that triangular plane. Should be uniform, but the way I drew it wasn't really good. Um, so what we can see is this is, first of all, this is 3D, so no Green's theorem. No Green's theorem. It is counterclockwise, however, and it is a surface. So the question is this conservative? Well, let's go ahead and check out the cross. IJK, DDX, DDY, DDZ. Let's see, it's going to be XY, YZ, and ZX. So if we cross the I portion, derivative of this with respect to Y is 0, derivative of this with respect to Z is Y. So it's negative Y. So we can already see that this isn't going to be conservative because I'm not going to get 0, 0, 0. Let's go ahead and just finish the cross anyway, but with respect to J, so it's going to be the derivative of this with respect to X is Z, derivative of this with respect to Z is nothing, so remember to change the sign so it'll become negative Z. And then the K part, derivative with respect to X is 0, minus derivative with respect to Y is X, so it's minus X. So it's not conservative. Not conservative. So that means no fundamental theorem of calculus. So it looks like, because we're talking about a surface here, we could do this. We could do this directly. If we do this directly, because it would have to basically be a C1, C2, and C3. We'd have to have 3 line integrals. And it wouldn't be terrible, but it would definitely be a bit of a pain. It would take a while. So maybe the best way to do this is to try Stokes. Let's see if that's going to work. So I have one surface. That's the plane. So I'm not talking about anything underneath of it. It is bounded by C. You can add all these up and just call it one big C. And it is positively oriented because that's what it tells us, counterclockwise. So we're good. We can use Stokes theorem. So we've got the integral of the line integral, f dot dr, is going to equal, the good thing is we've already found the curl of f dot n ds. And again, I'm writing it like this because this is the way that AACC wants you to write it. So what are we going to need? Well, we're going to need the curl of f. We have that. We're going to need n. We're going to need the normal vector. So we need to go ahead and parameterize this thing, which means we need the equation of this plane. And I'm not going to spend a lot of time going through that, but what you should basically be able to see is if these are your intercepts, to get 1, 0, 0, 0, 1, 0, 0, 0, 1, your plane is going to have to have been the equation x plus y plus z equals 1. I mean, you could certainly go through and develop the plane in another way, but that seems pretty straightforward in this case. So we can use the trivial parameterization that x equals x, y equals y, and then to solve for z, just subtract the x and the y. And now we've parameterized this thing with the trivial. So we'll do r sub x, which is 1, 0, -1. R sub y, which is 0, 1, -1. And then we're going to need the cross. Rx cross Ry. So if I eliminate this row, I'm going to get 0 minus minus 1, which is 1. Getting rid of this one, we're going to get -1 minus 0, but change the sign, so that's 1. Getting rid of this one, 1 minus 0, so that's 1. Okay, and that's positive, so it's outwardly oriented, which is good. This right here is our normal vector. So Stokes' theorem says I'm going to take the double integral over our surface of the curl, which is this, dotted with this normal vector. Well, dotting this with 1, 1, 1 is just going to give us minus y minus z minus x. But I'm going to replace the negative z with its parameterization, 1 minus x minus y. So minus 1 minus x minus y minus x dA. And this one is really nice. This negative y minus a minus y, that's gone. This is positive x when you distribute the negative here, minus x, that's gone. So all I have left is the double integral of the surface of -1 dA, which if I factor out the negative is the negative double integral over the surface of 1 dA. And if you guys remember, this is the same thing as the area of D, which is the domain under the surface. But don't forget that negative. So it's really the negative area of the domain. So if we take a look real quick at what the surface looks like underneath, well, that's just this section right down here. It's this. That's the domain underneath of the surface. So if you kind of put that back into an XY orientation, it's literally just that triangle. 1, 1. That's X, that's Y. So the area of that triangle is 1/2 base times height. 1 times 1 is 1, times 1/2 is 1/2. So what I get is that this is -1/2. Now you certainly could have worked through and, set up the parameters, done a double integral of 1, but you would find out it gives you the same exact thing. So again, just showing you a different way to work the problem. All right, number 7. This will actually be a short one, and number 8 will take a little more time. Number 7 says we want to find the integral of f dot dr. It gives us that circle right there, which means that it is a closed, counterclockwise oriented, and it even shows it to you in the figure. It's closed counterclockwise. So it's two-dimensional, so as soon as I see that, I'm thinking Green's theorem, and hopefully that will work. So this is 2D, closed, and it's good to list all this stuff, and positively oriented. Green's theorem. Let's do that one. So remember, to do Green's theorem, we need dq dx. The derivative of the second piece here with respect to x is going to be, bring that out front, 4xy plus 2. dp dy. The derivative of this piece with respect to y, that's 0. This is going to be 4xy plus 2. That is really nice, because remember that Green's theorem is the double integral of dq dx minus dp dy dA. dq dx minus dp dy is 0, so we get the double integral of 0, which is nothing. Very, very nice problem. That one makes us happy. All right, last problem. So this one's a little bit different. And there's a reason I'm showing this one. We want to evaluate as you can see, it's over a surface of f dot n ds. So this is going to be some kind of a surface integral where f is defined as yxz. We want to let s be the portion of this paraboloid above the xy plane. So if we kind of sketch what that one looks like, and you do need to know these sketches for the AACC exam. So you're talking about a paraboloid which is above the xy plane. Looks like it's got an intercept of 1. Something like that. It'll look something like that. But this thing's got a z-intercept up here at 1. The problem is, whoops, there, that's a little bit better. The problem is this thing is not closed. It's just talking about the portion of the surface above the xy plane. So it's really talking about this piece up here. That's our surface. In this case, we're going to call that surface 1, and you'll see why in a second. So one option 1, is we could do this directly. We could calculate the surface integral directly. You could use a trivial parameterization, x equals x, y equals y. In this case, z is already defined as 1 minus x squared minus y squared. And then you could find your normal vector by doing rx, ry, crossing those. You know, we could do that whole process. So we could do that. But there's another option, and this is the one I'm more interested in. This one's not horrible, by the way. It does work out. I believe the answer actually is pi halves. If you work it out, you just have to take my word for that, or you can try it yourself if you want to. The second option is we can actually use the divergence theorem. Now I know you're probably thinking, if you remember the criteria, well, divergence theorem, the surface has to be closed, which means we'd have to include this bottom, but it's not the case in this. The divergence theorem, because you'd have to have the entire region E within this surface, but since it's not closed, we don't really have that. But that would be the same thing as this. If the bottom was part of the surface. If the bottom was part of S, which it isn't. However, what we could do the following. We could take the divergence of F and we could subtract this bottom disk, this bottom surface right here, which now I'm going to call S2. And that's this piece that we would traverse that way. Now it's not actually included, so what we could do is we would take the divergence, which would include it, and then subtract off the surface integral of that, because it wasn't really supposed to be there in the first place, over S2 of f dot n ds. So we're really going to combine a couple of different things here to do this. So what we're doing is we are going to make it closed and subtract the part we added. And again, this is just another method, another way to do it. So if we wanted to, let's go ahead and figure this out. So the divergence, remember the divergence is del, so it's ddx of this first piece, that's nothing. ddy of this piece, that's nothing. ddz of this piece is 1. So the divergence of f is 1. So the base of this thing is circular, so it's going to be best to do this in polar. Best in polar. All right, so our triple integral over e of 1 dv is going to be 0 to 2 pi for theta, 0 to 1 for r, and then remember it's z because it's technically cylindrical, but I said polar, but it's really cylindrical. Z is going to go from, well, whoops, z goes from this surface, which is z equals 0, up to some place on the curve. It's going to vary depending on where you are, but the curve is defined to be 1 minus x squared minus y squared. So z is going to range from 0 to 1 minus x squared minus y squared, but the minus x squared minus y squared part in polar is the same as r squared. So it's going to be 1, which we don't need to include, but remember we do have to do the conversion factor because we're not parameterizing, we're just changing into cylindrical. So it's r dz dr d theta. All right, so there are no thetas involved right there, so that's going to be 2 pi. I do still have an r in here, and this bound right here is in terms of r, so I can't separate those. R dz dr. So we're going to do this first of all with respect to z, so it's going to be rz from 0 to 1 minus r squared dr. Still have my integral from 0 to 1 and 2 pi. So plugging in 1 minus r squared here is going to give me 2 pi integral 0 to 1 r times 1 minus r squared. Plugging in 0 gives us nothing. Save one step here. Distributing the r is going to give me r here. So the antiderivative of that's 1/2 r squared. Distributing the r here is r cubed. So it's minus 1/4 r to the 4th from 0 to 1. 2 pi. So plugging in the 1 is 1/2 minus 1/4. Plugging in 0 is nothing. 1/2 minus 1/4 is 1/4. So I get 2 pi times 1/4, or pi halves. And you might say to yourself, wait a minute, I thought you just said the whole answer was pi halves and we haven't subtracted off anything yet. You're absolutely right. Which means that when we do the surface integral of this disk down here, better be 0, because we need to get pi halves out of that. So we still need to find that just to verify that we've done everything correctly. So the surface integral for S2, we will need to parameterize this. So it's going to be x equals, again it's a disk, so we're going to do it in polar. So x is going to be r cosine theta to make sure we're traversing this thing counterclockwise. Y is r sine theta. And since z is just sitting there on the xy plane, z is 0. So r sub r would be, cosine theta, sine theta, 0. R sub theta is going to be negative r sine theta, r cosine theta, there we go again, 0. And now we're back to an arrow. Weird. Strange. All right, so r cross r theta. So if I eliminate this, I'm going to get 0 minus 0. If I eliminate this one, I'm going to get 0 minus 0. If I eliminate this one, we get r cosine squared plus r sine squared, which of course is just r. Now this is actually bad. I don't want this one, because r is oriented, upward. And to have used, goodness gracious, and to have used Stokes' theorem, we need this thing to be coming down. We need it outwardly oriented, so we need everything to be pushing down, which just means I took the cross product in the wrong order. So we're just going to really say r theta cross r is going to be 0, 0, negative, negative r. And that one is the one that we want. That is now outwardly oriented. I'm going to fix that r. All right, I think we've got everything we need now. So the double integral over the domain of, well, considering that this is going to be dotted with our function, so the function part, I don't care, and I don't care because it's going to be dotted with 0 and 0. And then the last part of the function was 0. Oh, this is wonderful, because now I've got this, this, oops, that should be negative, negative r, which is perfect, because now the dot product is 0, 0, 0. The dot product of this thing is 0. So I'm going to end up with nothing. So indeed, we do get that pi halves minus 0 is pi halves. Whoops, come on, let's finish this off. There you go. All right, didn't quite make 20 minutes, 21 minutes, but close enough. All right, that's everything. Enjoy.